So welcome to the fourth video of this video series. In our last video we designed a pile cap which was square in nature. Today we'll be looking at a triangular pile cap. Okay, so let us begin. So the question says that there is a column of size 350 by 350 millimeter carrying an axial load of 500 kilonewton, and this column is supported by three piles. Okay, the diameter of each pile is 400 millimeters. The grade of concrete is M20 and the grade of steel is Fe415. So now let us look how the pile cap will look like. Okay, so I have got three piles over here. This is the first pile, second pile and third pile. Now if you join the centers of all the three piles, you will see that it forms a triangle. So I have named this triangle as ABC, A, B, C. Okay, and the midpoint of side BC I have taken as D. So this is the midpoint and I have marked it as D. Now you can see that there is a square over here. This is the square, green colored. Okay, so this square is actually the column. Now we know that the column is carrying an axial load of 500 kilonewton. So I have denoted that axial load by P. So P in our case will be 500 kilonewton. Now an interesting thing is this column is actually located at the CG of the triangle ABC. Now when I say CG, CG means center of gravity, and we know that the center of gravity of a triangle is at a height of 1 by 3 from the base of the triangle, right? So that means this CG is at a height of 1 by 3 from point D. Okay, now let us look at the size of the pile cap. We know that the minimum spacing between two piles is 3 times the diameter, right? So in our case the diameter of each pile is 400 millimeters. So if I take 3D, it will be 3 into 400, that is 1200 millimeters. In meters it will be 1.2 millimeters. So this is what I have denoted over here. 1.2 millimeter is the distance from the center of two piles. Okay, similarly here also I have got 1.2 meter, and here also I have 1.2 meter. Now if you have watched my previous video, I have said that there is something called minimum overhanging distance. So what is overhanging distance? It is the distance from the edge of the pile to the edge of the pile cap. Okay, so if you see, this is actually the edge of the pile and this is the edge of the pile cap, and I said that the minimum overhanging distance is taken as 150 millimeters. Okay, so now if I want to calculate this distance from here to here, then how do I calculate it? It will be equal to 150. Okay, this distance 150 plus the diameter of the pile, that is 400, plus another 150. Okay, so if you add all the three terms, you will be getting it as 700 millimeters. That means it is 0.7 meters. Okay, so on all the three sides you will be having 0.7 meters. Okay, so this is actually the shape of the pile, the black color one. So this black color one is actually the shape of the pile. Okay, now if you look at triangle ABC, okay, if I want to calculate the height of AD, suppose I want to calculate AD, then how do I do that? You know that triangle ABC is an equilateral triangle because all the sides are having a magnitude of 1.2 meters, right? So this is an equilateral triangle, and in an equilateral triangle each angle is of 60 degree. So it means that angle ACB is 60 degree. So if I take AD by DC, it will be equal to tan of 60 degree, right? Tan of angle ACB. So if I look at the second step, I write that AD is equal to DC into tan 60 degree. And what is DC? DC is actually half of BC, because I told you that D is the midpoint of BC, right? Now I know the value of BC because BC is the center to center distance between two piles. So BC is 1.2 meters. So ultimately if I solve this, I get the value of AD as 1.04 meters. Okay, now it's given to you that the load coming into the column is 500 kilonewton. Okay, so now for the self weight of the pile cap, I assume that it is 10% of the load coming into the column. So 10% of 500 will be equal to 50 kilonewton. So if I add both of them, the total load will be 550 kilonewton, which I denote by PT. Okay, now observe very carefully. If I look into the actual diagram, I consider a beam from point A to point D. Okay, so the beam will be starting from point A, it will pass through the column and it will reach point D, right? So I have told you that the load from the column or the column is at the center of the triangle CG. So this distance will be how much? This distance will be 1/3 of the height of AD. Yes. So this situation is represented over here. Okay, so here I have got point A, I have got point D. Okay, and here I have got the load coming from the column, that is PT. PT is 550 kilonewton. Now you see that PT is at a distance of 1/3 from point D. Okay, so I have written that it is 1/3 AD. So if it is 1/3, then obviously the other side has to be 2/3 of AD. Now from our previous calculations, we have already got that AD was 1.04 meters, right? So I can obtain the value of 1/3 of AD. So you will find that it turns out to be 0.347 meters. Similarly, you can calculate the value of 2/3 of AD, which will be coming out to be 0.694 meters. So now since you have known the distance between all the points, okay, you can calculate the reactions developed at point A and at point D. So the reaction at point A I have denoted it by RA, and the reaction at point D I have denoted it as RD. Okay, so if you take moment about A, you will be getting the values of RD. So RD comes out to be 367.01 kilonewton and RA will come out to be 182.9 kilonewton. Okay, so now I know the reactions of the beam. So if I know the reactions, I can draw the SFD as well as the BMD. Okay, so these are the SFDs and BMDs with their respective values, right? Now here what I do, instead of taking the beam from point A to D, I am taking the beam from point B to point C. Okay, so the situation is represented over here. Now in between BC I have got point D, which lies exactly at the middle of BC. Now you see, I know the reaction developed at point D from the previous slide. Okay, so the reaction developed at point D was 367.01 kilonewton. So this reaction will be acting at BC, right? So I can write RD is 367.01 kilonewton, or you can say that this is the load coming into the beam BC. Now you can calculate the reactions developed at point B and C. RB, if you see, it will come out to be 183.50 kilonewton, and RC, that is reaction at C, will come out to be 183.50 kilonewton. Okay, if you know the reactions, again you can draw the SFD and BMD. Okay, so here we need to determine the effective depth of the pile cap. Okay, so for this we use this famous equation mu equal to 0.138 FCK BD square, where mu is the ultimate moment. So if you rearrange, you get this equation: D is equal to root over mu by 0.138 FCK B. Now the big question is, what will be the value of mu? Now mu is the moment greater, or you can say it is the larger value between the beams AD and BC. So if you look at the bending moment diagrams, you will see that the bending moment, the maximum bending moment for AD was 126.93 kilonewton meter, and for beam BC it was 110 kilonewton meter. So obviously beam AD is having the higher bending moment, so I consider that. Okay, so I have considered 126.93 kilonewton meter. So if I solve this, I'll be getting the effective depth as 314 millimeter. Now I adopt the overall depth as 1000 millimeter, slightly higher, so that I'm on the safer side. Now what will be the revised effective depth? It will be 1000 minus the clear cover, that is 50, minus half of the reinforcement dia. So I have considered the reinforcement dia to be 16 mm bars. Okay, so this is the effective depth, that is 942 millimeters. So once I know the effective depth of my pile cap, I can determine the reinforcement required in the pile cap. Okay, so I'll be looking for the beam AD since it is having the highest bending moment. Okay, so I first calculate mu by BD square. Mu I take again 126.93, and I see that the value of mu by BD square turns out to be 0.30 Newton per mm square. So now what I do, I use SP16, and that too table number 2 of SP16, from where I get that the percentage of steel required is 0.085%. But let me tell you that the minimum percentage of steel as per IS 456-2000 is 0.2%. Okay, so from the point of bending moment, the percentage of steel required in my pile cap is 0.2%. Okay, so next let us see how much amount of percentage of steel is required from shear point of view. So for this we first calculate what is the shear stress acting on your beam, that is we calculate tau V. So you know tau V is Vu by Bd, where Vu is the ultimate shear force. Now if you look at the shear force diagram of beam AD, you will find that the maximum shear force is 367.01 kilonewton. So I have considered that to be my ultimate shear force. Okay, so if you solve this, I get tau V equal to 0.83 Newton per mm square. Now you know that tau C should be always greater than tau V, so I have adopted the value of tau C slightly higher than tau V, which is 0.85 Newton per mm square. Now note that this value is adopted from table number 19 of IS 456-2000, and from the same table I get to know that the percentage of steel required for tau C equal to 0.85 is 2.25 percentage. Okay, so this percentage is higher than the one which we obtained from bending moment, right? So for bending moment we needed 0.2%, but now we need 2.25%, so obviously we will be providing this percentage of steel. So let us calculate what is the area of steel required in your pile cap. So if you solve this, that is 2.25% of the gross sectional area, you will be getting this much amount of steel required in your pile cap. Okay, so once you know the area, you can also determine the numbers of reinforcement required. Okay, so total area divided by the area 1 bar gives you the number of bars required. So you get a value of 73.79. So what I do, I provide 75 numbers of 16 mm bars which are spaced equally. Okay, these are spaced equally along AD. Now this arrangement can be also adopted for the side BC as well. So hence I have written that provide 75 16 torr spaced equally along AD as well as along BC. Okay, so here you can see the arrangement of the reinforcements. Okay, so I have got 75 numbers of 16 mm bars along the direction of AD. Okay, so these bars, the vertical ones, are along the direction of AD, and similarly along the direction of BC also I have got 75 numbers of 16 bars. So these bars are actually along the direction of BC, right? So all these bars are equally spaced and arranged. Okay, so this is how I do the design of a triangular pile cap. So that's all for today. Thank you.